Well, thanks everybody for coming out on a rainy Friday. Welcome to the first meeting of the math club this semester. Hopefully, there'll be a lot of good. We got some interesting speakers already lined up. We're still building the calendar, but oftentimes I kick off the math club, and I'm going to kick it off today with a talk that is. I mean, I don't want to insult your intelligence. Everybody in this room is sophisticated enough to put together this talk. It's very simple. All you need is, well, a calculator app on the phone, pretty much. But it's interesting to see connections here. So I want to start off by playing the following game. By the way, let me ask you all this. How many of you, so everybody in this room, so majority of me, how many of y'all had calculators growing up or ever use it? How many of you in high school, do they still use graphing calculators in some classes? I find that kind of interesting, right? Because you can find better apps on your phone, and there's certainly stuff on the internet that's better than what you get on those grainy graphing calculators, right? So I'm going to play this game here. I'm going to stack checkers in the following. So I've got a checkerboard with it looks like 64 squares here. 2 checkers, 4, 8, 16, doubling it every time, right? Until bottom right corner, I finally stack 2 to the 64 checker. This is like that old thing about, you know, giving somebody a penny once a day or and double it every day. So assume that my checkers 1/4 of an inch tall. Right, so that's a ½ inch, that's an inch, that's 2 inches or something. Now, I double my checkers, fill up the board. That final stack in the bottom right, 2 to 64 checkers. Somebody ballpark for me how high that stack of checkers is. Round figure, ballpark. Is it past the moon? Past the moon? I mean, you know, why do you have to just, you know, just kind of ease into it a little bit? Is it bigger than the, I don't know, the Empire State Building? Well, probably, right? Jared offered Beyond the Moon, right? What do you think? Is Jared too much? Is over the top? Is he not enough?
I think it's Pluto. Under Pluto. That be part?
What's Pluto? I think didn't they start? Kind of drummed out of the academy. Yeah. To Pluto, what do you think? This is just checkers, folks. Let me tell you. So let me kill the suspense. We got to guess Pluto and the moon. Can anybody tell me what a light year is?
Inches?
Huh? No. What a light year is. Right, it is a distance, so it's actually, this is kind of a common misconception. It is actually a measure of distance. It's how far a beam of light would travel in 1 year, right? So for perspective, light goes about 186,000 miles per second. So that's like 7.5 times around the Earth at the equator every second. The sun is 93 million miles away. That is about 8 light minutes. So if the sun blew up, we've got 8 minutes to party down before it's all over, right? So the nearest star to us that is not the sun is about 4.3 light years away. The stack of checkers will reach to that star and back, and then back again. It's almost 13 light years long. That isn't that surprising that, this happens just over 64 steps. Let me ask you this. You all know what, sure. You know what the factorial means, right? Right. This doesn't just mean 5, it's 5 and 4 and 3, you can count down, right? So let's play the same game. The factorials. 1, 2, 6, 24, and this would be 64 factorial. Now, let me point out something about 64 factorial when you're figuring out the number of checkers. When I was a wee tyke, I used to go over to my dad's office and I would play with his calculator sometimes. He was an architect. But this is back in the 70s, and he had like, a 1970s calculator. And I remember I used to play with factorial, but 69 factorial was the largest factorial that my dad's calculator could handle, right? At 70 factorial, it went over 10 to the 100th power, which the calculators back then couldn't handle. Nowadays, no problem. But back in the day, at 70 factorial, it would return error because he'd gone over. And 69 factorial, my dad's calculator in the 70s could stomach it. So 64 factorial, even my dad knows what this is. Now, how about this stack of checkers? Beyond Pluto?
It'd probably be beyond the observable. The observable. Yes.
So, how many of you know what the Andromeda Galaxy is? But it's a sister galaxy of ours, a little bit bigger. It looks like a fried egg, right? It's actually amazing. It's about 2.5 million light years away, but it's about half the size of the full moon in the sky. It's just very, very big. But you all see, right? It's like Utah. You've seen pictures, right? Everybody knows what the Andromeda Galaxy is, right? So, round trip to the Andromeda Galaxy is about 5 million light years. So at 64 factorial checkers, each of a quarter inch apiece, that stack of checkers will reach to the Andromeda Galaxy and back 17 billion times. That is a lot of checkers, right? I mean, that is a very big number. So I'm going to give you one more kind of thing of this ilk here. I had a friend when I lived in Fargo, and she was very good about getting like sort of stimulating books for her kids, science, that sort of thing. And so she had gotten this book for her kids about mathematics. And there were things like this that I'm talking about in the book, and they would talk about interesting math things to get people all juiced up about mathematics instead of turning them off. And I was reading the book because it was pretty well written and it was fun to read. I was reading the book one day, and they were talking about a Google. How many of you know what a Google is? And I don't mean spelled this way. You know what Google is? That's where Google actually got its name, and when it's spelled different. So it's the smallest number that my dad's old-fashioned calculator could handle. It is 1 followed by 100 zeros, right? This is a Google. So they were discussing Google in the book, and the author talked about being at like one of these kind of book reading things that he did as an author. And he talked about a Google, and somebody asked him to give, how big is a Google? And the author said, well, it's very big, which is certainly true. And he said, it is greater than the number of raindrops to fall on Scotland in the past 100 years. And when I read it, I laughed, and my friend asked me why I laughed at it. And I said, well, clearly the author is correct, but I think it is a great, great missed opportunity. And so she challenged me to figure it out. So I did a little computation as the way I roll. Let us suppose Scotland is 32,400 square miles. It's actually a little bit smaller than this, but I wanted to be honest. So I rounded it up to 32,000. By the way, why did I round it to that number? Because I'm a lazy man and it's a perfect square. It's 180 square. So Scotland's actually a little bit smaller than this, but let's suppose that Scotland is 32,400 square miles. Now let's assume, so we're gonna model Scotland as a box. 180 miles square. So I wanted to make sure that I was okay with this. So I assumed that it rained, and not just the silly wintry November rain, but a pretty hard rain. So I assume rainfall of 200 raindrops per square inch per second. Constant. So assume that it's always raining at 200 raindrops per square inch per second. I just made this up. I actually went and looked it up later. Most meteorologists classify torrential raindrops at 113 drops per square foot per second. This is like God with a Scotland-shaped fire hose, right? I mean, that's what this is. I mean, this is a waterfall, right? But nonetheless, let's go with it. We're going to assume this anyway. So if you assume that every second it rains 200 raindrops per square inch per second on Scotland, which is 180 miles by 180 miles, how long would it take for a Google of raindrops fall? Anybody want to guess? So I'm fire hosing it 180 square miles, 200 drops per inch per second. How long is it going to take me to hose that down with a Google of raindrops? So I'm going to do this in terms of age of the universe. And I don't mean what you read in Genesis either. I mean 14 billion years. Okay, so 14 billion years is 1 unit of the age of the universe. It would take 870 billion times the age of the universe to hose down Scotland with a Google rainfall. So that's a big number. Can we all agree on that? Right. So I think it's kind of surprising that numbers that we can write in a very sort of economical form can be so surprisingly big when you look at it from a certain perspective. Okay, so let's see. Got me. So 18. Yeah. All right. Okay, so the first thing I'm going to ask you. So I did promise the probability of this. I'll do this. How many of you have ever heard of the Monty Hall problem? Right. So is anybody not familiar with the Monty Hall problem? So there was an old game show from the 70s called Let's Make a Deal. People would come on dressed up in chicken suits and all kinds of crazy crap. It was really kind of silly. But what would happen is they would bring the guests up, and there were 3 doors. doors number one, door number two, door number three. Okay, and I'm doing this is kind of a basic probability, but it's a segue to what I'm going to do in a moment. So I got three doors, and here's what you know. Two of the doors have goats behind them. And one of them has a prize, like a car or something like this. Right. Of course, what you want is, I'm assuming that you don't want the goat, that you actually want the car, the $10,000 or whatever. So here's what would happen. The host knows which door the prize is behind. This is important. And the host never, and in earlier iterations of this problem, there was some deceptive things that went on because it wasn't clear. But the host does the following. Okay, come up and I say, okay, Charlie, which door, and the goats aren't necessarily behind one or two. Charlie, pick a door.
Three.
Okay, Charlie may have picked the right door or not, right? But let's suppose that, well, Charlie picks a door, and what I do is that leaves two doors. One of those doors has a prize and one of them has a goat, or both of them have goats, correct? So I've got a goat behind one of my other two doors. And me as the host, to add heightened tension to my game show, I open up one of the doors and show a goat. And I've got this option because these are either both goats or at least one of them's a goat, right? And then after I showed the audience, oh, it's good that Charlie didn't guess one because it was a door there, I go to Charlie and say, okay, Charlie, are you sure? Do you want to stick with your guess or do you want to change doors?
Change.
Does it matter?
Yeah.
It absolutely matters that you change doors. In fact, it doubles your chance of winning, right? Can anybody explain why this should always be the strategy given the parameters I've given you?
Has to do with the fact that those knows where the goat is.
Well, right, yes.
Well, if we pick the strategy of always changing doors, right? We have 2 or 3 times of winning. That's picking a quote in the first place because the other door mandatory is the card. On the other hand, just staying with the door that you pick in the first instance, you only have 1/3 of winning the prize.
That's right. The host inadvertently or advertently gives you information in this. When Charlie said door number 3, right out of the gate, what are the chances he's right? 1/3. That's straight up, 1/3. What are the chances he's wrong? 2/3. So there's a 2/3 chance that that goat is in one of those other two doors. And what does the host do? He shows you one of the goats, right? So now that 2/3 probability is concentrated on the only door that hadn't either been picked or open, right? Charlie's 1/3 on his initial guess and 2/3 on what's left over. This actually caused a lot of consternation, and it's kind of a simple basic, but it's non-intuitive, right? Most people say, it doesn't make any difference. By the way, I guess that means you should probably switch, right? Because if it really doesn't make any difference, there's no harm in switching, right? So why not roll the dice, right? Even if all my probability is rusty, but go ahead, switch. Okay, so let me ask you another question. So I'm going to do a head count. One, we had some other, 7, 30, 16, 30. I get 30 people in this room. So, actually, does anybody, I hope this is true. Anybody born on February 29th? Okay, so I'm going to pretend that there are 365 days a year. So we're going to forget about those 4 folks. All right, we got 30 people, 365 days in the year. What are the chances that at least 2 of us in here have the same birthday? Yeah. Anybody want to guess what the probability is? I think a lot of people would guess like 1/10 or 1/12.
76.
I think if I counted, bro, we got 30 in here.
30.
What's that?
70 maybe, something like that.
That's awful high, isn't it? Actually, it did. Yeah, actually, good shot. It's about a 70.6% chance. Does that seem, I mean, we're not even covering a physical calendar. How can this be? Right? You want to test it? I've done this many times. I'm doing a good part. I am curious myself. So I tell you what, I'm gonna go, I'm gonna point at you, y'all's birthday, tell me what your birthday is, and if anybody's got it, and not year too, but just the birthday, if anybody else has got it, just holler and tell me to stop.
The day of the month or just the day?
The day and the month.
Okay, October 14th.
August 8th,
June 30th.
February 27th.
July 14th. August 4th.
June 13th.
March 16th. September 9th.
Oh, I think we need to have people speak up, well, let's start again. Let's speak up so that everybody can hear.
October 14th.
August 18th.
June 30th.
February 27th.
July 14th. May 21st. August 4th.
June 13th.
March 16th. September 19th.
That's his birthday.
Right, and it may have occurred, more often as well, right? So, of course, there was almost a 30% chance that nobody pairs up. But, actually, it's probably better than 70.6%. But why is that? I mean, I tell you, I had given this little problem in parts of lots of sort of public talks that I do, and I always do what I just did. And I'm waiting for the date, but I've never been burned. Of course, I could always, got the very last person to say, oh, that's my birthday. So, why is it that only covering the group of us together don't even cover a 10? We don't even cover a 12 of the calendar. Yet it's very probable that we still see a birthday. Think of it this way, and this is similar to the goat thinking. Now, let's imagine, let's kind of do this piece by piece, right? If I am going to say, well, there's no two people in here with the same birthday, how can I be incorrect in that statement? Many ways. You two have the same birthday, right? But maybe you three had the same birthday, or you two and you two. There's lots and lots of different ways that at least two people have the same. And it's too many for me to count. It's too confusing, right? What makes me right? What has to happen for me to be correct that no two of you have the same birthday? Every single person in here has to have a different birthday. So let's think about what that entails. And again, I'm going to simplify this by assuming that there's only 365 days. We're going to forget about February 29th. Imagine walking people into a room one at a time. The first person walks in. What's the chance that whatever that person's birthday is unique in this room? 100%, right? Now, when you bring in the second person, what's the probability that the second person misses the first person's birthday? He's got. Now, when you bring the third person in, the third person's got to dodge two birthdays. Agreed? And then you do this like 29 times. Everybody okay with it? Now, I'm sure that a lot of you, if you showed up at a math club, have played around with calculators. What happens if you start taking powers of a number that's less than 1 even if it's pretty close to one. So 364 out of 360, that first fraction, 364 out of 365 is about 0.997. Right? Now what happens if I take that to the 29th power? It starts to decay pretty quickly, right? In fact, the 29th power of this, I got 0.92. Right? Now, that doesn't seem to miss by much, but what else is true about this when I multiply this out? This isn't just the 29th power of 364 365. These numbers are actually getting smaller, right? And when you get down to, whatever it is, maybe 305 or something out of 365, that's like 0.9, not 0.9, right? In fact, it's quite less than that. So these numbers decay rather rapidly. I mean, look at like even something like 0.99 on your calculator, start taking powers of it, and it starts dropping. So this drops rapidly. Whatever. And by the time you get out to 29, this thing is about roughly 0.3. So if I take 365 over 364, 364 over 365, 363 over 365, 362 over, and multiply all those all the way down to 305 out of 365, I'll get about 0.3, right? So the only way for me to keep all your birthdays different, that's only 0.3. That's the only way to do it. And so that means that whatever's left over, all the different ways that at least two people paid up on a birthday, that's 0.7. Everybody okay with that? Now, I'm going to do a more dramatic example of this. But first, I'm going to ask you a very silly question. Comparison. Here's my silly question. Where is my silliness? Okay, so here's what I want to do. Let's assume that the earth is flat. Professor Davis, no, it's not. Simon and Dan, don't put up videos about it. But I'm just doing this for my mathematics. Now let's suppose that we build a bridge. What I want to do is I am going to dig a hole in the earth that is a perfect cube. And it is going to be, what is my cube going to be? It is going to be about 648 miles. 648. 648. And this is why I pretended that the earth is flat, because otherwise I'd have to worry about the curvature. By the way, that's about the distance. So it would be like digging a hole if you started at Clemson to Toronto. So as the crow flies, it's about 650. So I dig this hole in the earth and I fill it with little cubes. Right? Just little, and the cubes are 1 cubic inch, right? So it's like I've got D&D dice and I'm filling this thing, and I will actually regular dice, but all of them at volume of 1 cubic inch. Every single one of these cubes is white, except for one that I let be red, right? So I fill this thing with as many as I can fit, white cubes, and there's one exceptional red one in it. Now, I put a blindfold on you, and I say, go out there in that pit of cubes, pick one at random. What is the probability that you pick the red one? I'm not going to compute this. Would everybody agree the probability is small? Right? Not zero, but you would have to, I mean, way beyond winning the line. Way beyond. Everybody okay with that? Okay, keep that in mind. 1 cubic inch red cube out of all the white ones in that big hole, hard to find. I'll ask you my related question. So here's my related question. So my related question is this. I take a mole of ink, so this comes to be about um, I take no. So this is about 3/40 of a cup or 3/5 of an ounce. So a small amount, right? And I carelessly toss it into the ocean, right? While I'm down at Myrtle Beach, throw it in the ocean. And I assume that the ocean gets mixed. So this all gets mixed in thoroughly with the ocean. So now the ink is uniformly distributed over all the oceans in the world, the Pacific, the Arctic, everything, right? 10 years later, after this is all distributed, I take the same size beaker that had the ink in it, and I dip it in the ocean in Hawaii, and I get just a random 3/5 of an ounce out of the ocean. What is the probability that at least one of those original ink molecules is in that vial? Anybody want to guess? And let me help you along. The distribution of those ink molecules in all the oceans is essentially the same as that one red cube in all the white ones in the 648 by 648 by 648 lines. What's the chances? Well, let's see if we can figure this out kind of naive. Let N equal number of molecules in the ocean. All the ocean, yes. And N, little n, is number of molecules. I mean, now what I asked is when I dip my beaker back into the ocean, what are the chances that I get at least one ink molecule? This is like the birthday problem, right? Imagine, good table problem. Imagine that I put those molecules in one by one. I'm picking my little molecules out of the ocean. What are the chances? And by the way, just kind of for perspective, if you will, N 6.02 2 times 10 to the 23. And so you're the perfect spectator for this. So Avogadro's number, right? And the capital N, according to nonpartisan sources on the internet, is about 4.5 times 10 to the 46. See, that's another thing. It's kind of deceptive, isn't it? Right? Because it seems like, oh, look, 23 versus 46. Well, it's not that much different, is it? But it is. So now imagine that what I do is I take my beaker and I start putting in molecules that I picked out of the ocean one at a time. Now, ocean has N plus N molecules. We'll ignore all the other trash that people have been throwing in the ocean since then. We'll just pay attention to our ink. But now our ocean has a slightly larger number, but I mean, little n is negligible, really, compared to big N. So when I put my first molecule in there, what's the probability that it's not one of the ink molecules? Well, I've got N non-ink molecules to pick out of N plus N total molecules, right? Let's put the second molecule in, shall we? How many molecules do I have now? Well, now I've got N minus one to pick. If I'm gonna make sure it's not an ink molecule, it has to be out of the original ocean. And just do this. 6.022 times 10 to the 23rd times. That's all we do. By the way, I did some, if we did this all the way down, and did this 6.0, I computed that if you had a computer that would do 93 quadrillion calculations per second, it would take about 75 days for the computer to figure out this product. So I need something else. So let me do this. Approximate by that. Now, if you remember back to when we were messing around with the birthday problem, I did this approximation for a small amount, right? And the actual product, those things we did in the birthday problem came to what, 0.3? My approximation came to 0.92, right? So it was off, right? Significant. This is going to be bigger than this, right? So this approximation is honest in a certain sense. By the way, what makes this perhaps easier to do? How do we go?
Easier to find.
What's that?
I mean, it's not so difficult to bubble one number to something.
Well, that's right. Yeah, with modern technology, it's pretty quick, but you can even do it by hand a little bit, right? Because this lends itself to computing stuff with log, right? So you compute the logarithm. So this is easier to handle for sure than this. And I did compute this, and here's what I got. So if I got so what I got was even over. This was about 0.0003163 change. And that's actually too big. So the probability of at least one is even though those 8 molecules are distributed the same as that one red one in that sea of white, there is more than a 99.97% chance that you will have at least one 8 molecule in there. And this is a sloppy calculation. It's probably a lot better than that. Yes, the distribution is really wide, but you have done this experiment so enormously many times that it's extremely likely that you will have gotten at least one of those molecules. And I want you to contemplate this problem that I've shown you the next time you share a swimming pool with some kid in a diaper. So, let me give you, kind of one last fun. Oh, by the way, any questions so far? All right, so I'm gonna give you some. This is, maybe I'll lie a little bit, so this one will help if you've seen some contests. But I am going to, let me start with this. So, how many of you out there have seen Calc 2, have seen sequences? How many of you have seen? So I apologize to my kids, but this actually, so you're adding up. What does it mean to add up infinitely many things? So I'll give you a crash course on this. Okay, so what does this mean? This is 1 plus 2 plus 3 plus 4 forever. Right? When we say this diverges, and if I was really sloppy, I shouldn't say this, but will anyway, it adds up to infinity. And what does that mean? Well, how do we determine if something adds up to something finite? We look, it's called partial sums. Like, well, okay, I think this is about 1. Oh, wait, 1 plus 2, 1 plus 2 plus 3, oh, 1 plus 8. So the partial sums are 1, 3, 6, 10, 15. What's happening to that sequence of numbers? To infinity. No matter what, if you walk up to me on the street, give me a number, 100, I can take that far enough and exceed what you think. Right? If you say 1,000,000, I can do the same. This also, this converges or diverges very slowly. 1 plus half plus a third. Give me any number, and this I can eventually add up enough of these that will exceed it. Right? And actually, this adds up to infinity as well. Any of you that have seen Calc 2, you know how you show this? So I'll give Calc 2 a plug. There is a really neat theorem that says under certain hypotheses, which this is good enough here, that to tell if this converges, all you have to do is look at the interval. And I'm going to use this in a moment. So what I mean is, this adds up to something finite, if and only if this adds up to something finite. Or I shouldn't say that, if this interval becomes something finite. They don't add up to the same thing, but in approximation. Anybody know how to indicate this one? Well, I'll write down the antiderivative and I'll make you groan. There's the antiderivative, right? Because the derivative of this thing is 1 over log x times 1 over log x times 1 over x, right? So it's a big fat sheet. And this is log, well, I should say the limit as t goes to infinity, log t minus log. This actually goes to infinity. So very, very simple. But again, if you give me any number, 1,000,000, 1,000,000,000, whatever, I can add up enough terms to this series, and it will eventually sail past it. Right? Give me 10, there's enough terms, it'll go past 10, and so on. So, this thing adds up to infinity in that sense. Take it far enough, and it'll get as big as you. So my question is, somebody estimate this. Okay, so first let me give you. Let me give you that. By the way, you might wonder why I start this at 3. It's just to make sure that this is a positive term series. I don't want to subtract it. But I didn't have to start at 3. The first few terms of this are approximately, the first term when you plug in 3 is about 3.226. The next one is about 0.55. And the next one is about 0.26. Right. By the way, I can give you a series with these first 3 terms like this that add up to things that are pretty small. How many terms does this say? Estimate. In fact, give me 2 integers. This is. And by the way, how many? I'm going to ignore the fact that we're term. How many terms we had? Anybody know what this is called? By the way, it's called Google Plex. It's 10 to the Google power. Let me also point out that you can't write this number down. I mean, you literally can't write a Googleplex down in ordinary notation because it is 1 followed by a Google of zeros. There aren't enough subatomic particles in the universe to write this number down in standard notation, right? That is, yeah. So I don't even know how to describe how big a Googleplex is. You can't even write it down in standard notations. So this is really lame, but I'm going to do it anyway. Let's assume that our universe has 10 to the 100 subatomic particles. By the way, that's about 1 trillion times 2. But go with me on this, because again, I'm a lazy. So let's assume our universe is 1 trillion times bigger than this. It's got 10 to the 100 things. Now, take every subatomic particle in the universe and turn that into a universe with 10 to the 100 subatomic particles. Now you've got 10 to the 200 subatomic particles. Now take every one of those and expand it into a universe of 10 to 100. Now iterate this process about 332 times. And now you will have a universe with about a Googleplex of subatomic particles. This is a very large number. So we are adding up an awful lot of stuff here. Would everybody agree? Anybody want to ballpark how big this sum is? Because remember, if I go to infinity, this adds up to infinity, right? So this is getting arbitrarily large.
51.
Let me show you kind of a neat way about this. Now, not to any scale here. This is my function f of x is 1 over x log x log x. And what I'm going to do here is see if I found something colored. Notice that the area of this box is 1 over 4 log 4 log 4. Because this is a little orange box, its width is 1 and its height is determined by this function, right? This box right here has area 1 over 5 log 5 log 5, right? And finally, I guess out here, this has 1 over n log n log n. And I like writing n better than the Googleplex because it's much easier, isn't it? Right? But that's what that symbol sort of means. So notice that which is bigger? The area under the yellow curve or the number of orange or the area of the orange boxes? Everybody agree that the yellow curve is bigger. So what I get here basically is my sum. 3 to n, where n is my complex. N log n log n is 1 3 log 3 log 3 plus sum from 4 n. So that's an equality, but this is the orange boxes. Right? So this is less than or equal to. One x. And this integral I just showed you how to do because the antiderivative, this is log x. So this is equal to 1 over 3 log 3 log 3 plus log n minus log 3. And you can actually, because I picked a googolplex, you can actually do log of n fairly easily calculate with all the sense. See, you never thought these things about log would be useful, but here we go. Right? This is log of 10 to the 100 log 10. Right? But the log is added here. So this is log of log 10 to the 100 plus log 10. Right? Splitting up this is log of this plus log of this. And I can suck that 100 down again. So this is log 100 log 10 plus log 10. And look how we turn what is a disaster, right? Something that you can't put in your calculator into something that looks run of the mill, right? The punchline of this, adding up all the subatomic particles in processing, this is about 11.03. Even though the whole thing has infinity, even a googolplex terms, it's still less than 12, which is absolute. And there's no subtracting. This is a positive term series. Kind of deceptive, isn't it? Because the first couple of terms get you past, the first 3 terms get you past 4. Okay. I think that is about all that I had to say. If you're graduate students, this is kind of a fun talk. I like to give this, and you all might not be as impressed, but trust me, do it to a lay audience, and you'll have them rolling in the aisles and stuff. So feel welcome to steal this. Any questions? All right. Yes.
Familiar with Lewis Carroll's pillow problem? I was thinking about that a month ago and stuff.
The pillow problem.
Yeah, it's a probability like thing. You used to think about is that so you have like a bag that you can't see into, and it has a ball that's either green or red with 50-50 probability. And so what he does is he says you have a red ball in the bag is either red or green. You don't know. You put the red ball into the bag, mix it around. You take the ball out, and you find yourself with a red ball again. Now, what is the probability that the ball in the bag is red? And it is no longer 50-50, despite the fact that all you did was put a red ball into the bag and take a red ball out of the bag.
I had a graduate student that used to get he would anger, I mean, this was his own problem that he would ask, but he would ask his problem, and then he'd get mad at me. It really angered him up. So here was his problem. In each hand, I had two arbitrary natural numbers. Arbitrary natural numbers, right? What is the probability that this one's the bigger one? 1/2, right? Now open your hand and look at this natural number. Now what's the probability that down there? He's making very angry. Okay. Any other questions? All right, y'all have a fabulous Labor Day weekend. We will not meet next week because I've learned not to compete with, you all know, I don't know if any of you freshmen, it's first Friday, next Friday. So they start doing the parade and so forth. So, you know, if you like that, great. If you don't like parades, I suggest you, as soon as your classes are over, scurry. But we'll meet in a couple of weeks after that. Y'all have a good weekend and we'll see you next time.